Welcome to the Combinatorics series. Combinatorics often gets a bad reputation for being confusing or difficult, in part because the word combinatorics is so unnecessarily long, when in reality it just means counting. That's it. All we're going to be doing is counting stuff. Another reason people say it's hard is because if you're not paying attention to details, it's easy to get stuff wrong. But if you are paying attention to details, you will maybe still get stuff wrong. But if you don't, it's really fun and really satisfying a lot of the time, because the tools and methods that we develop are going to allow us to solve really complicated problems in surprisingly elegant, beautiful ways. But before I can show you that beauty and convince you that I'm not truly insane, let's start with something a little bit simpler, okay? So consider the string ABC. A string, by the way, is just a sequence of letters in some order, right? It's like ABC. Here's your first question. How many rearrangements of this string are there, including this one? Or in other words, how many ways can I shuffle up the letters A, B, and C and put them in some order, including this order? Take a second to think about that. In fact, maybe you want to pause the video and take a few minutes to think about that, but definitely don't continue until you have a numerical answer to that question. Okay, well, how do you do something like this? Well, in a simple situation, and this is a relatively simple situation, one thing you can do to count all the outcomes is just to list out all the outcomes and see how many things you listed, right? So we can just make a list. The first thing on our list is ABC because we are counting that particular string. And what else is there? So we have CBA, we have ACB, we have BAC, we have BCA, and we have CAB, and then that looks like everything. So that's 1, 2, 3, 4, 5, 6 outcomes. So that's the answer. Now, do you have any criticisms at all of what I just did? Well, how can I be sure that I didn't forget something? I kind of just listed everything out, and then once I couldn't think of anything new, I stopped and thought I was done, and then just counted what I had, and I had 6. How could I be so sure I didn't forget something? Just so you know, just so in case you're paranoid, the answer is 6. I did not forget anything in this particular question. But I could have easily forgotten something if the question was more complicated or the answer was much bigger, right? In general, listing things out is a bad idea. Because if the answer is really big, even if you didn't forget anything, if the answer is like 10 to the 100 or something like that, you're never going to finish listing that out, ever, okay? But even if the answer is not big, most of the time, even if you have the time to make the list, you're probably going to forget something, given the answer is pretty big, okay? Even if you're really smart, you might forget something. And if you forget one thing, you are completely wrong. Your answer is completely wrong. So, how can we not forget something? It seems like an impossible thing to accomplish, to not forget something. Well, the right way of thinking about this is actually to eliminate the strategy itself. Like, forget listing things out. That's the problem. We need a better strategy. And in part, what makes a strategy good is it should give you confidence that you're not missing anything and that it's right, that it's just completely right. There's a lot of strategies in combinatorics. In fact, that's kind of what combinatorics is. It's like the art of collecting these strategies. But the main strategy that you're going to be using, and a lot of strategies are sort of based off of this one, it's something called divide and conquer. Which basically means that you take a problem, a big problem, and you divide it into smaller problems, and then you conquer each of those small problems, and then you use that to answer the whole question. So, what does that look like in a combinatorics problem? Well, the way that you divide the problem is you want all the outcomes that you're trying to count, before you count them, you should try to organize them in your mind. You should try to put them into groups. And that way, you're less likely to forget something, because if everything belongs to a clear group and you have all the groups, then you shouldn't be forgetting anything, right? So the first thing is you want to group the outcomes into different categories. It's actually really hard to do this well, okay? Sometimes it's easy, but sometimes the very thing that makes a problem really hard is to group outcomes the right way, because there's so many random ways that you can group outcomes together. And like learning how to do that well is something that you'll get better at with practice, okay? So we're gonna group outcomes. The second thing is we're going to count the outcomes in each group, and then we are going to add them all up. By the way, you can visualize this strategy a little bit by, if you think about this as the region of all the outcomes that you're trying to count, then grouping outcomes is kind of like you're cutting up this region into pieces that are hopefully easier to count. Each piece shouldn't be that hard to count. That's why you do this, right? So in this situation, you'd have 1, 2, 3, 4 pieces. You would count each piece, and then you would just add them all up. And that's what divide and conquer is. It's pretty simple. But there's 2 mistakes that you might make, okay? So when I say group outcomes, you have to be very careful that your groups are good. What does it mean? What does that mean? The first thing is you don't want to forget any outcomes, right? That's the whole reason that we don't like listing things, is because it's easy to forget outcomes. The way that you group outcomes, the way that you come up with your groups should make it so that every outcome belongs to some group, okay? That is called, the word for that is exhaustive. Your groups are exhaustive if all outcomes belong to some group, like you're counting everything. Another thing that you need is you don't want your groups to overlap with each other, because then you're going to have the opposite problem of undercounting, which is what you would have if your groups were not exhaustive. You're going to have the problem of overcounting. If some outcomes belong to multiple groups, when you add together those counts for those different groups, you're going to be double counting, potentially worse, certain outcomes, and your answer is going to be too high. So we want the groups to be what's called mutually exclusive, meaning there should be no overlap between them. Okay, so we want mutually exclusive groups. How can we apply that to this problem? Just as an example. Well, how can we group the outcomes? Like how all of the ways that we can rearrange the string ABC, how can we group the outcomes into different categories? Can you think of any way of doing that? Well, I think the most natural way to group them is to think about the first letter. What are the possibilities? Well, it has to be an A, B, or a C, right? Those are valid groups. Like the first letter is an A, the first letter is a B, and the first letter is a C. So like A dash dash, so like A, and then we don't know what those are, and then we could have the first letter as B, or we can have the first letter as C. And these, so now we have 3 groups, right? So we group the outcomes into these 3 groups. Are they exhaustive? Yes, that they do count everything, right? Like every arrangement here is going to fit into one of these categories. Are they mutually exclusive? Yes. You can't have an outcome that's in both of these categories because it's impossible for the first letter to simultaneously be an A and a B. And so these are valid groupings. And so how many ways can we do this one? So if the first letter is an A, this could either be BC or CB. There's only 2 possibilities for that, right? And you should feel very confident that that's true, that if the first letter is A, there's only 2 ways to finish this off, BC or CB. Similarly, if you start with a B, there's AC or CA. So there's 2 ways you can do that. And then for C, AB or BA, so there's 2 ways you can do that. So the answer is 2 plus 2 plus 2, which is equal to 6, which agrees with our original answer. But this approach should hopefully make you feel more confident that we didn't forget anything. Just so you know, problems can get way harder at the snap of a finger. Here's a little bit of a spicier problem. So instead of starting with ABC, let's start with SPICY. How many rearrangements of this string are there including the original. Take a moment to come up with a numerical answer to that question. I will wait. Okay, well, if you did the listing method, I am so sorry. That must have been horrifying. Let's try to divide and conquer it, like we just talked about, okay? So let's, again, divide and conquer based on what the first letter is going to be. So it could either be an S, a P, an I, a C, or a Y, right? So it could either start with an S, a P, an I, a C, or a Y. Now, this is already starting to feel a little bit daunting because there's 5 cases and each of them has 4 slots to fill, and it seems like things are getting harder as opposed to easier, maybe. But is there something that you can say about the number of outcomes that are going to be in each of these 5 cases? Like, which one's going to have the most outcomes or the least outcomes? Or can you say anything about that? Well, if you think about it, if you start with an S, it comes down to ordering PICY. If you start with a P, it comes down to ordering SICY. The number of ways you can order PICY and SICY, shouldn't they be the same? Because there's nothing like fundamentally, intrinsically different about a P or an S. They're just distinct characters. Any 4 distinct characters there should be the same number of ways of ordering them in some way. So regardless of which letter we start with, we're going to be left with 4 distinct letters that we need to put in some order. And so it follows that the number of cases in each, or the number of outcomes in each of these cases is going to be equal. So we don't actually need to do 5 different things. We can just address one of them and multiply the answer by 5 because that's the number of cases that there are. So the answer to the question, is 5 times the number of strings that satisfy any one of these cases. So we can just pick this one arbitrarily. So who cares about these cases? We could just do 5 times this case. So how can we do this case? Well, how can we count all the strings that start with an S? Well, we can kind of divide and conquer again, right? Like we can divide and conquer based on whatever that position is going to be. So that can either be a P, an I, a C, or a Y. So we could either have SP with 3 unknowns after that, or we can have SI with 3 unknowns. We can have SC with 3 unknowns, or we could have SY with 3 unknowns. And by the same logic, if you think about it, if we start with SP, it's coming down to ordering 3 things, ICY. If we start with SI, it's coming down to ordering 3 things. It's just a different 3 things. And so the number of ways that we can fill out each of these cases is actually also the same. So again, we can just pick one of them, count it, and then multiply the answer by 4. So let's just pick this one. So who cares about these cases? We can just say the answer is going to be 5 times now 4 times the number of things that satisfy SP dash dash dash. And then by the same logic, we can just keep on doing this, right? Like we can do cases again on, well, actually, we've already answered the question with ABC of how many ways there are to order 3 things. It's 6, right? We already got that. It's 6. So the answer to this is just 6. So the answer is just 5 times 4 times 6, which is 20 times 6, which is 120. Notice that we multiplied numbers here instead of adding things together. So we tried to do divide and conquer, which is about adding things together, but we realized in that process that each case or each group had the same number of things in it. So we only need to count one of the groups and then multiply it by the number of groups that there were. And then we actually use that sort of over and over again to get this sort of nice, clean looking answer. And because of the fact that we're multiplying these numbers, this type of method where you divide and conquer in such a way that each group has the same number of elements, that strategy is more specifically called the multiplication rule. if you can design groups in such a way that you can leverage the power of the multiplication rule, that is ideal, okay? Another way that you can think about this is with a tree diagram. So, you know, for the first choice for which letter is your first letter, you can think about that as, you know, you can start with an S, a P, an I, a C, or a Y. And then once you choose an S, you have 4 choices that come out of that, a P, I, C, or a Y. And then from P, you have 4 choices. From an I, you have 4 choices. From a C, you have 4 choices. From Y, you have 4 choices. And then once, so like, you know, this might be like a P. And then from that P, you're going to have 3 choices, right? And then one of those is going to be an I. From that I, you're going to have 2 choices. One of those is going to be a C. And then from that C, you're going to have 1 choice. And this particular path, S, P, I, C, Y, is going to correspond to the original order, right? And so you're basically just counting sort of paths from the root of this tree to a leaf, and each of those is going to correspond to a particular outcome you're trying to count. And this is one way of visualizing the multiplication rule. And in particular, you'll see that this is the same as 5 times 4 times 3 times 2 times 1 if we continued the logic instead of using the fact that we had already solved it for ABC. And we get this kind of number a lot, starting with an integer and multiplying all the way down to 1, so often that we have a notation for it. 5! It's actually 5 factorial, okay? So that is pronounced 5 factorial, and it means 5 times 4 times 3 times 2 times 1, which is also the answer to this question. The last way of kind of visualizing the multiplication rule is with a slot diagram, which sometimes applies, where you can think of the 5 slots that we're trying to fill with the letters S, P, I, C, Y. And in the first slot, we have 5 choices. We can put down any of S, P, I, C, or Y. And then here's the important thing. Regardless of what you choose here, regardless of your choice, you will have 4 choices for that slot. That's kind of what we were talking about, right? No matter if I pick S, P, I, C, or Y, there's going to be 4 choices I have for this slot. So 5 times 4. So for each of these, I have 4. So that's why I'm multiplying. And then for each of those 20 things I could have done here, no matter what I do, I have 3 choices for that slot. I have 2 choices for that slot. And I have 1 choice for that slot. So that's a final way of visualizing the multiplication rule. Let's do another problem. So we can do a simple divide and conquer for this problem, right? We can consider the 5-digit binary strings that start with a 0 and those 5-digit binary strings that start with a 1, and then we can add together the results. But instead, we can actually realize that regardless of whether we start with a 0 or a 1, the number of outcomes in both cases should be the same, because both of them just come down to counting how many binary strings there are of length 4. And once you simplify it down to that, you can kind of do the same thing over and over again. And I'll leave it to you to try to unpack that on your own. But honestly, the best way of doing this type of a thing is with a slot diagram. So if you have 5 slots, which we do for a binary string of length 5, for the first slot, we have 2 choices, a 0 or a 1, right? So we have 2 choices. For the second slot, regardless of what we chose for the first one, we have 2 choices, a 0 or a 1. So that leaves 4 combinations so far for the first 2. And then regardless of which of the 4 things we choose for the first 2 things here, there's 2 choices for that, a 0 or a 1, which leads to 8 choices so far for the first 3 things. And we can continue like that, right? Regardless of what we choose for these 8, or from the 8 things that it can be any of 2 things here. And then regardless of what we choose of the 16 things that it can be any of 2 things there, which leads to our final answer of 2 to the power 5, or 32. The last way of visualizing this is with a tree diagram, which I'm definitely going to run out of space for here because 32 paths is kind of a lot. But we can start drawing it, right? So for the first binary bit, right, for the first one, we can choose 0 or 1. And then from there, we can choose 0 or 1, right? So far there's 4 paths, or 2 times 2 so far. And then from there, we can go 0 or 1, 0 or 1, 0, 1, 0, 1. So already the tree is getting pretty big and I'm out of room, so I'm going to stop. But, you know, you can see that there's 8 paths so far, which corresponds to how many binary strings there are of length 3, or how many ways you can fill out at least the first 3 slots here. And this path would correspond to filling out 0, 0, 1, for example. All right, let's try another one. For this problem, I'm going to jump straight to a slot diagram. So, of course, when you're using a slot diagram, it implies that you are using the multiplication rule, just like we did in the last problem. And the multiplication rule is just a more specific instance of the divide and conquer technique. So, but of course, to use the multiplication rule, you have to be able to use the multiplication rule. And so what allows you to use it is when each choice you make doesn't affect the number of choices you have for each future choice. So for the first position of the employee ID, there's 26 possible choices, right? You can choose any letter. And the reason we can use the multiplication rule here, or the slot diagram here, is that regardless of what you choose, you have 10 choices for what digit comes next, 0 through 9. And the reason we can use the multiplication rule is because regardless of what we have chosen for this 26 and for this 10, there are 10 choices for what that can be, 0 through 9, which gives us the ability to use the multiplication rule, but also the answer to the question, which is 2,600. That's 2,600 different possible employee codes. However, that's less than 2844, which is the number of employees, and that means that not everyone can get a unique code, right? So, tough luck.